All right, so 3.5, derivatives of trigonometric functions. Now, I know that trig can be a scary thing, and I want to sort of remind you that it's okay to take a moment and breathe through the panic of seeing sine, cosine, tangent, all of those again, okay? Um, but just because, no matter how it went the first time for you in trig, if it went really well, that's awesome. If it didn't go so well, I'm so sorry. But there are always opportunities to continue to improve on that. And I think that might be for some of us a goal, maybe a short-term goal of saying, even if I see sine, cosine, tangent, I'm not going to shut down right away. Okay. Or the second or the third time, right? I've heard third time is the charm. But before we get there, okay, before we get to all those, let's take a look at what we know, all right? So as always, we will lead with our strengths, think about what we know and how we can use that to continue to build on other things, all right? So over on the left, I have put down a bunch of rules that we've learned so far. There are no names with these rules, but let's see if we can connect the rule to what is the output. All right, so let's start with d dx of c. If I take the derivative of c, c being any constant, what do I get? We get 0. Good, good. So we'll write a 0 here. And then in blue, what is the name of this rule? Good. The constant rule. Okay. All right. What about d dx of x to the n? How would we generalize this rule? Excellent. All right. So we bring the power down, we keep the variable, and we lose 1 from the power. And that is our notation for power rule. Okay. All right. What about d dx of c f of x? How would we write that as a generalized rule?
Is it c ddx f of x?
Yeah, we could write it that way. C, and then we could say d dx of f of x. And we could call that the constant multiple rule. Exactly. Constant multiple. All right, this is good so far. These 3 rules, in case you can't tell, we use them so very often. And I think it's important to know not just the rule, but also the name. So when folks are talking about them, you know what they're talking about, okay? All right, what about this fourth one? d dx of u plus or minus v. All right, so we could write this in a number of ways. Maybe we could write it as du plus or minus dv. That would be absolutely right. Exactly, and because we are adding them, because we are adding or subtracting, we've got the sum or difference rule, and we can just split them apart, okay? Now that is not true for the last 2 rules that we have here, right? We cannot just split these last 2 apart. But what do we need to do if we see d dx of u and v, u times v? Okay, what do we get, folks, when we apply that one? All right, so we are looking to use that rule, yes. And so we can say u dv plus v du, or the other way around, and we can call that the product rule, okay? And last but not least, looks like we've got a quotient rule over here. Anybody remember what that quotient rule is?
V du minus u dv divided by v squared.
Good. Now I will say this, and this does depend on sort of what your trajectory is, meaning what, like how many more math classes are you going to take? But if you are planning to take any future math classes, I know that we're remote right now, which means that you don't have to memorize as much, but these rules get used so often. If you are planning to take Calc 2, I would make sure you know these rules very, very well. Okay, same thing. If you're going to be taking Calc 3, I would make sure you know these rules very, very well. All right. All right. So what's new? We're going to be looking at the derivatives of the trig functions. Okay. So with these derivatives of the trig functions, I did ask you to kind of take a preview with that trig activity on Desmos from Monday. And so I'm wondering if folks remember any of those derivatives. Let's see how many we can list out. You can go in whatever order you want, but let's see if we can get all 6 of these based off of what we did on Monday. Cosine x for the first one, I agree.
Minus sine.
Yeah, nice. Negative sine x. Good, good. These are really important ones to know. All right, the sine and the cosine one comes up quite a bit. And yes, tangent, the derivative of tangent is secant squared x, okay? And just to be clear, secant squared x is the same as if you took secant of x and you squared that whole thing. And you're out. Okay, these are honestly the 3 most common ones. Anybody know the other 3? Nope, not a negative cosecant tangent. You're close though. Yeah, negative cosecant x cotangent x, yeah. Good, good, good. Secant x tangent x. And one more here, one more, last one. What is the derivative of cotangent? Nice, negative cosecant squared x, which is the same as saying take cosecant x, square it, and then make it negative, okay? All right, now these 2 are also good ones to know, okay? And I know, again, we are remote right now, so there's a lot less emphasis on the memorization. However, I do want to prepare us for the fact that at some point we might go back in person, and your instructor, depending on who that may be forgiving or not so forgiving about how much you have memorized. Okay, so that is something kind of important to think about, especially if you're taking multiple classes beyond this point. We will talk about some ways that we can help ourselves remember these a little bit better. I always find it easier to remember patterns rather than memorizing just a bunch of letters. Okay, so we'll talk about some tricks that I've used and also that students have shared with me over the last many years, and hopefully some of those will be useful for you. Okay. All right, so let's do this. let's kind of switch the order today. I know typically start with like where things come from. All right, so you can see here I've left a space for the formal definition of the derivative. I've even given you a little link to a visualization on Desmos, okay? But I'd say let's jump into some problems while our brains are a little bit fresher. And then at the end, I'll leave it sort of optional. Those of you who are very curious to know where these rules come from, we'll take a look at where the rule for sine and cosine come from. Okay, so we'll kind of do that a little backwards today. We'll get those problems out of the way, focus on some of that computation piece, and then we'll come back and think about why these things are the way they are. Okay. So we'll skip this for right now and we'll go right to example 1. Okay. So example 1 says d dx of 5x cubed sine x. And before we do anything else, one habit I would love for us to get into is determining which rule or rules we're going to need to use. Okay, because now we're going to be looking at a lot of different combinations of rules. And so we want to make sure we list them all out and we know how to set up a problem. Okay, so who's got a guess? What rule might we want to start with here?
Product rule.
Product rule, you got it. Product. Okay, and the giveaway might be that invisible multiplication sign between 5x cubed and sine x. Okay. All right, so product rule, if we write out the rule, okay, we know that we're going to need u dv plus v du. And so because we need u du v dv, we want to make sure that we have a setup. All right. So we're going to let u equal 5x cubed, and we're going to let v equal sine x. All right. So take a moment. Think about what du is. Think about what dv is. All right, and let's see what we have for du and dv.
Du it's a 15x squared. dv it's cosine x.
Good, 15x squared, and the derivative of sine is going to give us cosine x, okay? Now, the more quickly that you can identify the rule and set the rule up, the easier the rest of the problem is going to be, okay? A couple summers ago, I taught Calc 1 in the summertime, and I had a few students who literally went to the textbook and did every single problem. He did very well in the course. He also spent hours upon hours upon hours. However, we were talking later after he transferred to his 4-year institution, and he was telling me that because he knew these foundations so well, it really helped him focus on all the new things he was learning. Okay, and so I know that the number of courses you take beyond this point will depend on the person, but if you think you're going to be doing a bunch of calculus, whether it's engineering or math, or some computer science, then it might be a really good investment in your time to just sit and do a bunch of problems, okay? So that kind of practice is really very, very valuable. But once we have our setup, we can go ahead and plug everything into our product rule, okay? And so we're gonna get u is our 5x cubed, dv is cosine x, plus sine x, and du is 15x squared. Okay. Now, as far as simplification goes, there's really not a lot that I want us to clean up here. Typically, we have our trig functions at the end, and we have our polynomials in the beginning. So I could just write this as 5x cubed cosine x, but for the second term, I would just take the polynomial term, move that to the front, and I would get plus 15x squared sine x, okay? I know that we could take out a 5x squared. You don't have to do that, okay? You can leave your answer as is, all right? This setup is where a lot of the points on an exam really lay, okay? So being able to set things up is the most important part. Can you identify the rule? Can you do the smaller steps accurately? Because 9 times out of 10, if the setup is correct, you're gonna get the correct answer, okay? So a lot of times it's not in all the other simplification, but it's the setup that was wrong, and then folks get the wrong answer. Okay. So how do we feel about this first example here? Product rule, a little power rule, a little trig. Just what you want at 8:30 in the morning, right? Okay. So if the cosine, I have a question in the chat about what if cosine was cosine x cubed? And do you mean cosine of x cubed or cosine cubed x? Okay. So I do want to actually, this is a wonderful, wonderful question. Okay. So what if we had something like this? Okay. We're actually going to take a look at this tomorrow. And for cases like this, if you've taken calculus before, we are going to be using a different rule called chain rule. Okay. Chain rule happens in basically every problem that you're going to see from tomorrow on out, okay? It is one of the worst days to miss in class. So I would make sure that you are here to learn about that chain rule tomorrow, okay? But I love that we've got a question that is just sort of thinking ahead and saying, what if something looks like this? And for right now, I will just say we're going to be using chain rule here, and tomorrow we'll talk more deeply about what that means, okay? All right, let's go ahead and take a look at example 2. All right, so we've got ddx of cosine x over 4x squared. Let's start with that rule identification and setup. What do we think we need here?
Quotient rule.
Yeah, you bet. We're going to need quotient rule. And if we write our quotient rule off to the side, we get v du minus u dv over v squared, right? Now, I know I've been doing this a lot longer than you have, but I still like to write down those rules for 2 reasons. One, the more I write it, the more it sticks in my brain. Muscle memory. I'm writing it, I'm making that connection in my brain, okay? The second reason I like it is because once I do my setup, I just have to plug it in to the right places, right? And so if I write down the formula and I have my setup and then I plug in things, I'm less likely to make a mistake. All right. And so that is another place where I've seen students tend to make mistakes is they might not write the formula down, they set it up and they try and plug it right in. And then sometimes they plug things in the wrong place. Okay. So think about that. If you're someone who tends to make that mistake, this is a good strategy to kind of prevent that. But it looks like with the quotient rule, we're still going to need our u and our v and our du, and our dv. Okay. All right, so our u in this case, it's going to be cosine x. Our v is 4x squared. I'll take the low hanging fruit here. dv is going to be 8x, but what do we have for du?
Negative sign.
Good, negative sine x. All right, so this, the negative sign in front of the sign is super, super important. Okay, super, super important.
I have a quick question, Professor.
Absolutely, what's up?
On the denominator, so the original question, if it was like 4x squared cosine x, would the v then be the 4x squared cosine x, or just still the 4x squared?
Are you saying if we had a cosine x hanging out down here?
Yeah, in the denominator inside the parentheses, just right next to the 4x squared, would that whole denominator be the v, or just
Yes.
the 4x squared?
The whole denominator.
Okay.
Yes, great question. All right, so whatever is, and maybe if we color code this, whatever is on the bottom is going to be your v. And similarly, whatever is on the top is going to be our u. Okay. All right, so now that we have our setup, let's plug everything into the rule. And again, I'm not super picky about the simplification. All right, more so, did we identify the correct rule and did we set things up properly? All right, so let's give ourselves a little space and we'll get v times du minus u times dv all over v squared. Okay. This right here to me is like 8.5 out of 10, 9 out of 10. Like you've done most of the work already. Okay. The only things that I might clean up here, the negative sign looks a little weird when it's in between two terms. So let's take this negative, move it to the front. Okay. And then the other thing I might do is I might take the cosine and just move it behind the 8x because we typically have our trig functions at the end. And so that would give us negative 4x squared sine x minus 8x cosine x. Exactly. Now, I'll tell you another reason why I don't typically have folks simplify the denominator. I've seen so many people write this correctly and then write this as their bottom when they simplify. And then I have to take off the point. Right? What happened here? Why did I write this in red? Why is that wrong?
The 4 needs to be squared also.
Exactly, exactly. So if I did want to simplify, that coefficient better be a 16 because the 4 is squared as well, okay? And so it's almost like I know you know that, but in the context, like the very last step of such a complicated problem, that's where we tend to sort of have tired brains and maybe we forget. So there's another reason why I'm like, just leave it like that. Like, I don't want to see the correct answer along the way and then an incorrect simplification. Okay, you would be sad about that too, I feel. So, all right, so we've got a little bit of mixing and matching between rules that we already know, product rule, quotient rule, power rule, some of the trig stuff, okay? And so those are good questions to just kind of practice a bunch on. And I think you can find those kinds of questions everywhere. Would there be a case when we would have to square the V? I think that's really more up to the instructor. So I will tell you, I don't really need you to square that. The one exception might be, let's say we had square root of x in the bottom, and then that was my v, and then I squared it. That might be nice to write as just x. Right. Well, that's probably the one exception I can think about. But if you are going to take Calc 2 or Calc 3, I would make sure to check in with your instructor to see like sort of what flavor of simplification they prefer. Okay. All right. Let's take a look at a problem that sort of ties in 3.4. All right. So let's talk about position might be defined by some trig functions, and how do we apply what we learned in 3.4 with these new rules that we're learning right now. Okay. So it says if S of t is 2 sine t minus t, so this is our position function. Okay, so that represents the position of a function at time t. Determine when the particle is at rest, right? And so we've spent a lot of time translating this piece. When a particle is at rest, we are thinking horizontal tangent of position. We're thinking slope equals 0 on position graph. But we don't have any graphs, so we are going to do exactly what Sophia said. We're going to find our derivative, and we're going to set that equal to 0. Okay, when we solve for t, that's going to tell us this is the time when that particle is at rest. All right. So I think this is a really good flow from using what we did in 3.4 to think about how do we interpret what it means to be at rest. Okay. All right, so let's do the work. Find S prime of t. Okay, so S prime of t, which will be our velocity function. What do we get when we take the derivative of 2 sine t?
2 cosine t.
Good, and this is a great example of that constant multiple rule. 2 times the derivative of sine. Good. What about this minus t? Oh, so close. We don't get 0, we get 1. Okay, because t is like our variable. And so when we're taking that derivative, we get a 1. Okay, yeah, good, good. All right, so I've got my S prime of t, my velocity. Now we have to set S prime of t equal to 0 and solve for t. All right. So we've got 2 cosine t minus 1 equals 0. And this is when it might be useful to bust out that unit circle. Okay, so unit circle. I know it's probably been a while, but before we get to the unit circle, our goal here is to really isolate cosine of t. All right, so if I want to isolate it, I'm going to add 1, and then I'm going to divide by 2. And I'll get cosine t equals 1/2. Okay. Now, depending on who your instructor was, like how we find this on the unit circle may or may not be clear to you. So let me write out in words like what you're going to be looking for on the unit circle. Okay. When you say cosine t equals 1/2, the question you're really asking yourself is this: what angle has an x value of 1/2? Okay. Now, just to be clear, the x value on the unit circle, that corresponds to cosine. Okay. So that's how I know that I'm looking for an x value. The 1/2 is the value I've gotten. So that's what I'm looking for. And now I have to find an angle, okay? Now, I do want to say that at this point forward, you are most likely always going to be working in radians, okay? So if we've not made that shift in our brains, we want to start to make that shift, that our answers should be in radians, okay? So I agree that 60 degrees or 300 degrees are the location. And if we translate those into radians, we get pi over 3 or 5 pi over 3, okay? So we can say that at t equals pi over 3, that is going to be one place where we have a cosine of 1/2. And separately, we could say t is 5 pi over 3 is another place that has an x value of 1/2, okay? But one neat and perhaps sometimes frustrating thing about the unit circle is you can go around the unit circle as many times as you want, okay? So as far as going around the unit circle, if you go around the unit circle one time, how many radians is that? Good, 2 pi, okay? So every time you go around the unit circle, you go another 2 pi. And so you might have seen this notation before where there's sort of like a plus 2 pi k, something like that at the end. Have people seen that before? Yeah, okay. And I'm going to do the same thing right here, plus 2 pi k, but let's talk about what that means, all right? This plus 2 pi k means go around the unit circle k times, all right? So the 2 pi is go around the unit circle. And the k is like how many times you want to go around the unit circle, okay? So that's what that notation means. Now, for those of you looking to maybe take other classes, sometimes we specify that k is an element, all right? So we have this sort of scripty e, rounded e, is an element of capital Z. Anybody know what capital Z stands for? It's okay if you don't. But this capital Z right here, this is, it's actually all the integers. So it's not the real numbers. That would be like a capital R. But with the capital Z, we're talking about integers. Now, I'm aware that the word integers doesn't have the letter Z in it. Okay, so I feel like they should have picked a different letter, but we have Z. So when you see that scripty Z, that means integers, okay? So if you want to feel a little bit more grown up about your notation, you can say K is in the integers. Integers, yeah, maybe that's what we should start doing. That'd be an easier way to remember that. Okay. So a little bit of a refresher on how we find things on the unit circle. Okay, so that would be an important skill. This piece right here is a very, very important skill. Okay, the stuff in the purple is kind of like bonus. If you already feel comfortable with that, this is one way that you can sort of make your writing look a little bit more sophisticated if you want. Okay. But if you don't want to write it, I think it's still important to know what it means so that when you're reading a textbook and you see this notation, you're like, ah, they're just saying K has to be an integer, okay? Why did the 2 not go to a 0? Ah, okay, so let's go back and unpack this because I think this is actually a very common misunderstanding. And that is, if I were to think about the rule I want to use here, this is the constant multiple rule, right? This is a constant 2 multiplied by a function sine t. And so one way that I could explain this is if we go back to the top where we reviewed all those rules, the constant multiple rule says I can take the constant out and then just take the derivative of the rest of it. So that's one answer to your question, okay? That often gets confused with the constant rule. Like those are different rules, constant versus constant multiple, okay? If you were going to use the constant rule, let's go back down here for a moment, that would mean you were thinking, I'm going to set this up like a product rule. Okay, so in last week's discussion, I asked us to kind of consider constant multiple versus product. This is actually a really good example of that. U would be 2, V would be sine t. If I wanted to use the product rule, this would become cosine, this would be 0, but I have to use the product rule. And when I use the product rule, I'll get 2 times cosine t plus sine t times 0. And that's why when we get to here, we only have the 2 cosine t. Does that make a little bit more sense? Okay, okay. So that was the purpose of one of those discussion questions last week, is like, we can use the product rule, but the product rule tends to be longer. That's why we use the constant multiple as sort of a shortcut, because every time we have a constant, that derivative is going to be 0. So one of the things in the product rule is going to go away. Okay. All right, so 2 pi k, 2 pi is just one time around the unit circle, right? So if we draw a unit circle, maybe like over here, right? Pi over 3 is like right here, okay? Now, every time I'm at pi over 3, I'm gonna get an x value of 1/2. Well, I could go to pi over 3. I could also go one time around the unit circle and then stop there. That would be if I'm just adding 2 pi. But what if I want to go around the unit circle like 4 times? Well, 1, 2, 3, 4, and then I stop. K would be 4 because I've gone around it 4 times and then I'm going to that pi over 3. Yeah? Okay. Exactly. And so because the question didn't say, oh, between 0 and 2 pi, it sort of left it open-ended. We do want to compensate for that fact and say, I know you're saying we can go around the unit circle as many times as you want. So let's write it as plus 2 pi k. Right? This is a good what if question. What if I only want to go halfway around the unit circle? And I want to stop every halfway around the unit circle. How would I write that?
One over 2k.
You just pi times k.
Okay. So 2 pi is one time around. So halfway around would just be pi. Okay. So if I have a plus pi k, then I'm going halfway around and stopping. If I have what 1 put in there, pi over 2, I would be stopping every quarter way around the circle. Okay, so that's all that notation means. The k is just like for all the stops, and then the first part is like where you stop, how frequently you stop. Okay. All right, we've got a few more examples here, so let's kind of work through those. All right, so we talked about these in the beginning, but I do want to sort of reframe these in a way that has been helpful for me to memorize these, okay? So I tend to think of them in pairs. And so let's pick a different color. So I start with sine and cosine. To me, sine and cosine are a nice pair. And it turns out that the derivative of sine is cosine, and the derivative of cosine is almost sine. It's just a negative sign. Okay. And so I think about sine and cosine as pairs because I use the other one in the derivative. All right. Now, this is kind of a silly thing, but what letter does the word cosine begin with? C, right? So cosine begins with a C. And is the derivative of cosine positive or negative? And it's negative. Wow, okay. All right. Find me another trig function on here that also starts with a C. Cotangent. Okay. And from above, we wrote that the derivative of cotangent is negative cosecant squared x. So this negative sign and this first letter is the C is sort of an interesting pattern. Well, cosecant starts with a C. What's that derivative? Looking back at earlier in the notes.
Negative cosecant x, cotangent x.
Good, negative cosecant x, cotangent x, good. So, whoops, one of the patterns that a student pointed out to me once upon a time was, well, if I can't remember if a derivative is positive or negative, if the trig function starts with the letter C, then those derivatives are going to be negative. It turns out that is true. So derivative of cosine is negative sine. Derivative of cosecant is negative cosecant cotangent. Derivative of cotangent is negative cosecant squared. Okay, so that could be one trick that you use to help you remember which ones are positive and which ones are negative. Okay. But another pattern that was pointed out to me by some former students is that kind of like sine and cosine come in pairs, we can actually find ones that are similar in structure. So if you look at the derivative of cotangent, all right, you get a negative cosecant squared. Which one of the other functions has something that's like a something squared? Yeah, tangent, right? So the derivative of tangent is similar. It is not cosecant, but it's actually secant squared x. And so some students found it helpful to kind of pair tangent and cotangent, that we knew that the derivatives of both of those was like something squared. We just had to remember which one was secant squared, which one was cosecant squared. Okay. And then last but not least, if we take a look at the derivative of cosecant, we've got a negative something times something. And if we look at the derivative of secant, we get positive secant x tangent x. Okay. And so one thing that students noticed about this was that this function, cosecant, is actually in its derivative, and secant is also in its derivative. Okay. Now, these are just a few of the patterns that you might find when you look at those, but I thought I would share those with you because those have been the most popular over the years in terms of like, how can we try and memorize all of these, right? What patterns do we see? How can we find our own patterns in a way that kind of makes sense to us, okay? So if you find any other patterns, throw them out in the Discord or throw them in the chat. I'm sure that you have peers that would appreciate ways to memorize, especially as this is just the beginning and we're going to learn a bunch more rules. Bad news bear. All right. Any questions about these 6 derivatives so far? I hope we're not feeling too overwhelmed with all of the letters on our screen right now. All right, well, let's go ahead and try working on some of these questions, all right? And yes, the more you carve out time to memorize, the faster the questions are gonna go for you, right? And so that might also be a component when you're thinking about a timed assessment. How can you make sure that you get a chance to focus on the questions rather than did I memorize something correctly, okay? All right, so let's take a look at example 4. If f of x equals cotangent x, find the equation of the tangent line at x equals pi over 4. So we've learned about tangent lines, and we had a formula for how we're going to write our final answer for the tangent line. And we just need to fill in the different parts, okay? So from yesterday, we might recall that a tangent line equation can be written as y minus y1 equals mx minus x1, right? And of these, all these letters, which ones did we fill out to have our final equation? Does anybody remember? Y1, X1, and M, perfect. So we are gonna need an X1, we are gonna need a Y1, and we are gonna need an M, okay? Now, we already have one of those numbers. Which one do we have? Yeah, we
Excellent.
have that, exactly. So right here, right off the bat, we've got X1 is pi over 4. Because they told us that's the point we're interested in, okay? What could we find next from here? I think everyone's got a little bit of a different strategy approaching these, but what would we find next? Okay, some people want to find y prime. All right, let's do that. So to find m, find f prime of x and plug in pi over 4. Okay, and specifically, we're going to do it in that order. We're going to find the derivative and then we plug in our value. Okay, so f prime of x, if f of x is cotangent x, what do we have for f prime of x? Maybe we should start with, is it going to be positive or negative? All right, well, cotangent starts with a C, so it's going to be negative cosecant squared x. All right. Now, it might be nice to rewrite this before we plug in our number. And what I mean by that is this is the same as negative cosecant x squared. Okay. And I think this way is a little easier to plug in the values that we want. All right. But maybe one additional step we should take here is, I mean, it's hard for me to look at a unit circle and be like, oh, this is cosecant, this is cotangent. But it is easier to look at a unit circle and find things like cosine and sine. Does cosecant relate to sine or cosine? Yeah, it relates to sine. And so we're going to do even more rewriting. We're going to write this as negative. Instead of cosecant, we're going to write 1 over sine. Okay. I think we're ready now to plug in our number. F prime of pi over 4 is negative 1 over sine of pi over 4 squared. Okay. Now, friendly reminder, 1 over something is a fancy way of saying reciprocal. Okay. Let me say that one more time. 1 over something is a fancy way of saying reciprocal. So all I need to do is find sine of pi over 4, and then I'm going to write the reciprocal inside here. Okay. So if we go to pi over 4 on our unit circle, and this time we want to look for the y value there, we'll have negative 1 over root 2 over 2. Okay. Now, this looks very complicated to simplify, but again, we're just looking for the reciprocal. What's the reciprocal of root 2 over 2?
2 over root 2.
2 over root 2, good. So negative 2 over root 2, and then I square it. All right. Order of operations time, should I square it first or make it negative? Exponent, good. So I'm going to square it first. So 4 over, what's square root of 2 times square root of 2? 2, good. And so this is really negative 2. And this is what I can replace for my m. Okay. Now we are most of the way there, right? Because I'm not so worried about the simplification here, right? We've clearly done a lot of other work already. The last thing we need to find is that y1, right? How do we find that y1? Yeah, we're going to substitute, and more specifically, we're going to take pi over 4 and we're going to plug it into the cotangent function. Okay, so f of pi over 4 gives you cotangent of pi over 4. Now again, cotangent is not an easy thing to find on our unit circle. Anybody remember another way of writing cotangent? There's a few, but what are some other ways to write cotangent? 1 over tangent, I agree. What else?
Cosine over sine.
Cosine over sine. All right. that's going to be the one we use because cosine and sine are very visible on our unit circle. Okay, so cosine of pi over 4 over sine of pi over 4. We look those up on our unit circle, we get root 2 over 2 over root 2 over 2, which means that y value is just 1. All right, so 1 is going to go in the place of y sub 1. And let me shrink this down a little bit so we can write our final answer underneath here, that we get y minus 1 equals negative 2 x minus pi over 4. Okay. Now I want to be really explicit here. All right. Our exams are non-calculator, which means that I expect to see this sort of thinking and computation in what you are showing me. Okay. If you tell me cotangent of pi over 4 is 1 and there's not that intermediate step, it looks very much like you used a calculator. Okay. Same thing here. If you're like, I know negative cosecant squared x is negative 2, and you don't show me those intermediate steps, that also looks very much like you used a calculator. Okay, so make sure that you go back over all that sine, cosine stuff to help you think about how we can find these values without a calculator. All right. Just like I've never taken a math class where I've not used factoring. Don't know how many, I've taken very few math classes where I don't use sine or cosine. Okay. All right, let's see, what kind of time? So same thing with that unit circle. I would say if you are, going to take a lot of future classes, it is worth memorizing that first quadrant for the unit circle. All right, but if this is like the end of the road for you, then let's just kind of get through it. All right, let's do one more problem today. All right, let's take a look at example 5. Over the interval 0 to 2 pi, okay? And so we can see here some of that notation we used earlier. I'm including 0, but I am not including 2 pi, okay? So over the interval 0 to 2 pi, when does y equals secant x over 1 plus tangent x have horizontal tangents? Now let's think big picture first. What's our strategy going to be? Before we start computing things, what's our strategy going to be? Or what procedures have we used that might be helpful? Yeah, we're going to set that first derivative, set it equal to 0. Okay. So find y prime. Okay. And I love how much we're thinking ahead. We want to use quotient rule. Excellent. All right, so we've got u equals the numerator, so secant x, and v is going to be the entire denominator, 1 plus tangent x. Okay. All right, du, dv. Are either of these derivatives going to be negative? No, they're both going to be positive because secant and tangent, they don't start with the letter C. Okay, so our derivative here, we're going to get secant x tangent x, and over here we'll get 0 plus secant squared x. Okay. Double check that setup, make sure it's good, and then you're going to plug things into that quotient rule. So y prime equals v du minus u dv over v squared. Again, building that muscle memory, and now I'm going to plug everything in. 1 plus tangent x, secant x tangent x minus secant x, secant squared x, all over 1 plus tangent x squared. Whew, it's a lot of letters. All right, so as per usual, let's go ahead and see what we can do to clean up the numerator. Okay, let's clean up the numerator, but we're going to leave the denominator as 1 plus tangent x, that quantity squared, right? So if I start to simplify, I'm going to get secant x tangent x plus secant x tangent squared x minus secant cubed x all over 1 plus tangent x squared. Okay. Now I see a fraction in my derivative, but I also know that because I'm looking for horizontal tangent, I want to see where this fraction equals 0. Do I need the whole fraction? I want to set this equal to 0. What is the only way that I can get 0 out of a fraction? Okay. The only way I can get 0 out is exactly if I take this numerator. If that numerator is 0 and the denominator is defined, then we're going to get a 0 out. So when I do this next step, set y prime equal to 0 and solve for x, I'm going to go ahead and only grab the numerator. Okay. So that's me sort of thinking ahead that the only way I can get 0 out of a fraction is if I set the numerator equal to 0. So we're going to get secant x tangent x plus secant x tangent squared x minus secant cubed x equals 0. All right. Now, I chose this problem because even though we use sine and cosine a lot in all of our other classes, for those of us who are considering moving on to Calc 2, secant and tangent actually come up quite a bit, okay? And so one of the Pythagorean identities actually involves secant and tangent. And we can use that identity to simplify this gross looking thing to make it look much nicer. And so what I'm going to do is I'm going to go ahead and factor out a secant from every single term. I get tangent x plus tangent squared x minus secant squared x. Exactly. Now Matt has put into the chat the identity we want to use, but if you look at what he typed, what happens when I subtract secant squared from both sides? Good, good. and that's going to equal 0. All right, but check out what we have here. We have tangent squared minus secant squared. What is another way of saying tangent squared minus secant squared, according to this identity? Ooh, so close. Yeah, it's going to be -1, right? Because we subtracted the secant squared, but we also have to move that 1 to the other side. And when we move that 1 to the other side, it's going to be negative. So this we can replace with -1. Okay. Well, that is going to give us secant x times tangent x minus 1 equals 0. All right, all that long piece of work, once we simplified by distributing and then using a Pythagorean identity, we're able to get down to secant x times tangent x minus 1 equals 0. Well, this makes it a lot easier for us to find the values between 0 and 2 pi that work. It turns out that secant x never equals 0. Okay, secant x never equals 0. So the only part that can equal 0 is the thing inside the bracket. So now we need to think about our tangent values. Where does tangent equal 1? And another way of thinking about that is, when is sine and cosine, when are they the same? Because everywhere they're the same, something divided by itself is going to give us 1. So where on our unit circle do we have sine and cosine that are the same? And I see we've got here pi over 4 is a value. And the other place that happens, which sometimes gets forgotten, is in quadrant 3 with 5 pi over 4, because they're both negative there. So a negative divided by a negative will give you that +1. Okay. And since we're only looking one time around the unit circle, we don't need to do that plus 2 pi k. All right, we can leave it as pi over 4 and 5 pi over 4. Okay. So I know these were pretty juicy problems here. Lots of trig, hopefully not too much trig trauma, but I think that I've tried to highlight some of the more common identities that come up again, how to find the values, and those would be important things to go back and study. Also valid things to ask questions about. I have some videos from my past trig classes that I'm happy to share with you if you'd like to watch some of those. So let me know. And I think we'll leave example 6 and 7 for tomorrow. Okay, so we'll finish example 6 and 7 tomorrow. All right, so folks, if you don't have any questions, you are welcome to take off. All right, have a wonderful rest of your day, and I will see you tomorrow.
Thank you.